So there's a concept called samskaras in spiritual practice. So samskaras are the impressions that are made upon your mind by your existence. So you grow up as a little baby and you see things and you learn how to be a human being in this world. And that learning affects how you perceive new information. And in some teachings, there's implications that these samskaras come from before you were born, maybe what we call the DNA. So just for the time being, forget what you think reality is, and we'll talk about what quantum physics explains about reality. We're going to speak about something called the Copenhagen interpretation. So remember 1905, for anybody who was here in the first talk, 1905 was the year that Einstein published 4 papers. One of these papers was on the photoelectric effect. One of them was on something called Brownian motion. So looking at the movements of things that are very small. And this work, among other pieces of work, laid the foundation for what became known as quantum physics. But it quickly left Einstein's hands, and he disagreed with a lot of the realizations that were being made about this aspect of reality. If things are quantized, what that implies. And so the Copenhagen interpretation is by a collection of talks and a collection of discussions between 2 people in particular, Niels Bohr and Heisenberg. And in 1927, they presented a series of talks that they collected and called the Copenhagen interpretation. And later they regretted the name because interpretation, some people took to mean an interpretation of quantum physics. They didn't mean it that way. They meant it to be the interpretation, the one interpretation of quantum physics. So there are other interpretations of the mathematics of quantum physics. Because remember, when we speak of these theories, we're speaking of a mathematical framework to describe the physical world. And we have to translate this into our own thinking and into our own language. And sometimes in the translation can be where we get stuck. So let go of thinking that things should be as we perceive them. Einstein in particular didn't like some of the ideas that came out of this interpretation. Famous quote is that God does not play dice, because we'll go into some of the details of this. And Richard Feynman, who was easily one of the most knowledgeable about the field of quantum physics, he came up with a way to bring quantum physics in tune with other aspects of physics. He said, I think I can safely say that nobody understands quantum physics. So you're in good company. So in a nutshell, some of the things that quantum mechanics lays out. First, everything is made of particles or of quanta. So at the very fundamental level, things are discrete, are quantized. Things like electrons, quarks, photons, gluons, all fundamental particles that make up reality. Reality is relationships. The only reason anything exists is because it interacts with anything else. Without an interaction, a particle may or may not exist, or could be anywhere in the universe. I'm going to say that again, just slowly. So without an interaction, a particle may or may not exist, or could be anywhere in the universe. And until it interacts with anything else, we don't know. It's a little bit peekaboo, like babies. So maybe the babies had a better concept of quantum physics than we do now. But it's a little bit peekaboo. But the thing is, the mathematics that we're describing here are extremely good at predicting experimental outcomes. It is the whole field of particle physics, and we'll talk about some of the implications of that. And the results create something called the Standard Model. The Standard Model tries to find the fundamental particles at the smallest level of materiality, that the building blocks of the universe. So that's the basic idea of quantum physics. So Heisenberg uncertainty principle is a foundational concept in quantum physics, and something, even if you're not a physics person, you may have heard of this name, Heisenberg uncertainty principle. It means you can know where something is or how fast it's moving, but you cannot know both precisely. There are other pairs of information, entangled pairs. So these are complementary pairs. Position and velocity, for example, or momentum in this case, are quantities that you can either know one very well or the other one very well. The more you know the position, the less precise its momentum becomes. So what the result of this is it makes things a bit fuzzy. So up until now, we've been talking about atoms and molecules as sort of ping pong balls stuck to each other and orbiting each other. This is a more accurate representation of something like a hydrogen atom, where these fuzzy collections of lights indicate the probability that an electron, for example, is in a particular orbit. So we don't know precisely where it is, but there's sort of a cloud of probability of where it could be located. So it sort of takes how we know reality, that things are solid. I'm here, I know I'm here, and I can know how fast I'm moving. There's no contradiction. But as we move down to a microscopic level, things change. Einstein didn't like this, and Erwin Schrödinger didn't like it either. And at this time, there was the mathematical proofs, but then there was a big tradition of thought experiments, trying to think out the implications of these problems. So this is where we enter something called a paradox. This statement is false, is an example of a paradox. It's both true and false at the same time. And if you're like my husband, you might be mumbling this for the next 2 days. So something is true and false at the same time. And this is where we come to when we start looking at the implications of quantum physics. So Schrödinger developed a thought experiment, Schrödinger's cat. There's all kinds of memes online about Schrödinger's cat. This is the experiment he proposed. So, like I said, a particle is nowhere or everywhere until it interacts. We don't know. So what he proposed, if this was in fact the way of nature, if we had a box with a radioactive material in it, and we had a detector over here that can detect the radiation, if it detects the radiation, this hammer smashes this glass of poison and kills the cat that's inside the box. If the box is closed, we don't know if this material released radiation or not. It is quantum mechanically uncertain until it interacts with something. And so he said, if this was the case, until you open the box, you have the cat as both alive and dead, which is a contradiction. But this is the sort of paradox of quantum physics, that things are both alive or both there and not there at the same time. So what it asks is that nature doesn't exist unless it interacts, which seems very counterintuitive. Because I really believe that when I don't see my friend who's behind me, that she's really there. And my experiences lead me to believe this is the case. If you look back at Galileo, he had a great quote. By denying scientific principles, one may maintain any paradox. So now, moving into the scientific principles, we're finding paradoxes and holding on to them. So where do we go from here?